Hello and welcome back to the third and final episode of Crash Course Statics. Okay, so it's the fourth video, but I'm counting 2.5 as a part of this episode. Don't blame me for not planning out this series before I started. But anyway, this is the episode where we will design and test a truss to see if all of this math actually works. One common design is a simple worn truss. This is used in all sorts of bridges and is essentially a bunch of triangles in a row. I wanted to do something that didn't look so simple and that was intentionally poorly designed. By that, I mean I wanted a single joint to be put under a lot of load. To do this, I shrunk the middle triangle of a worn truss. It's not a practical design, but it meant I would need less weight to break the bridge. I based this off my own intuition after having worked with statics. However, intuition is not always reliable. So it's time to get into the math. So here is my test setup. I'll have the bridge span between two supports with bars on either side to keep it from tipping over. I needed these bars because the truss was designed in 2 dimensions and as a result was unstable in real life. The bars created some friction, but considering my scale is only accurate within a pound, friction's not that big of a deal. I attached the weight to the middle of the bottom support. Now, this is something we didn't cover in the introduction episode, but it's actually not that complicated. The weight downward needs to be countered to keep the member from moving, and to keep it from rotating, the force must be the same on both joints. This means that one weight in the middle of a member is the same as 2 smaller weights at the joints. Of course, if the beam becomes the weak point rather than the joint, then this is no longer true. That's beyond the scope of this video, however, so we can simplify the problem and use this diagram with 2 forces of P, with P being half of the weight we use. For the time being, I will keep P as a variable and try to solve for the force on the joint that we plan on testing. That joint will be made out of a match, which I tested in the previous half episode. I decided to put the match in the joint at the top of the center peak. Unfortunately, we can't immediately calculate the load that would be on this joint. It has 4 attached members, and thus 4 unknowns, as well as no known values. The bridge is symmetric about this point, so that's really only 2 unknowns, but without any known values, it's still impossible to solve for the load here. Even the joints where the loads are applied have too many unknowns, so we have to start all the way out at the support. If we imagine the bridge as a simple object, then we can find that each support must be lifting with a force of P. This is because the bridge as a whole is being pushed down with a force of 2P at its center. It's just another static equilibrium problem. Fortunately for us, this bridge is symmetrical, and so is the loading. So we only need to do the math for one side. We can start by balancing the forces in the Y direction, because there's only the support and one member with the Y component. Like in the last episode, we represent the angle of this member with a fraction. In this case, it's 5/4. We also have to remember the sign convention for tension and compression. This first member is in compression, making its force of 5/4p negative. For this problem, we don't have to find the force on the second member to get to the point we want. So let's save some time and ignore it. Next, we have to solve for both unknowns at the peak of the first triangle. All 3 members have x and y components. So we actually have to solve for the force on the first in terms of the force on the second. Then we can use the other direction to solve again. This lets us find one member's force, and then we go back to the previous equation, and that gives us our second answer. If you really want to get deep into the math, go ahead and practice on your own. I know you're probably all dying to solve some equations this summer. So now we have one of the forces on the joint in question. Due to the symmetry, that's actually 2 forces, and we can extrapolate the other 2. I summed the forces in the y direction, solved, and we get, whoa. Oh my. Well, if we plug it into a calculator, we can approximate that upper member has a force of about 3p, and that the bottom has half of that, with 1.5p. Clearly, the highest force is in the upper member, and the joint is also constructed such that the match is in single shear. All of this means that the bridge should collapse when the upper member is exerting a force of 17.6 pounds. That force was found in episode 2.5 by repeatedly breaking matches. In that episode, I also mentioned the factor of safety. A factor of safety just means that you assume the force is greater than it should be to give yourself room for error. I found that a factor of safety of 1.5 gives us a safe load of 11.73 pounds. Using these two numbers, I found that we can safely put about 8 pounds on the truss for the test. Then I can increase the weight until the bridge breaks at about 11.7 pounds. Okay, that might have caused some confusion because the total weight to break the bridge is basically the same as the safe shear load. That's because at the joint in question, P is multiplied by about 3, but P is actually about half of the weight we're putting on the bridge. That means that the load at the joint is close to 3/2 of the weight in our bucket. That multiplier also just so happens to be the same as our factor of safety, which is 1.5. This is just a coincidence. If I chose a factor of safety of 2, then the weight required to break the bridge would still be 11.7 pounds. But the safe load would change. Hopefully I didn't make that any more confusing. Finally, we are ready to actually test the bridge. So let's travel back in time to December when I actually did this test. Okay, so this is an 8-pound load onto the middle of this member. This should not break, if my math is correct. So let's lower it down. Let go. And there we go. 8 pounds is hanging off the bridge. So that's going to be it for this video. I proved math works because it didn't break. So I guess I'll see you guys next time. Like, comment, subscribe. I'm kidding. We're going to break it. Basically, just proving that something doesn't break at the workload doesn't prove that the math was correct, so there might be other problems. So let's validate our model here and load this till it breaks and see if it's about 11 or 12 pounds. I'm going to start adding water slowly until this fails. Here we go. It's slipping. Is that it breaking though? I'm gonna look at that joint. That's under a lot of pressure. Okay, hopefully this isn't the thing that breaks. Okay, yeah, it just had some friction on the wood. Ha! A successful test. Just ignore that part where I touched the bridge right before it fell. I think that just released some of the friction I mentioned earlier. Overall, I think it was pretty successful despite the bending issues with our two-dimensional bridge. And it was cool to actually be able to predict when this bridge would break fairly accurately. I didn't think of this at the time, but I could have built an identical bridge that was connected in parallel and simply doubled the load. This would have kept the math the same, but would have kept the bridge from falling over. So if you want to break your own model bridge, I would recommend doing that. Also, try to make it smaller so it doesn't bend so much. But anyway, that's where I'm going to leave this series. This was just the tip of the iceberg when it comes to statics, but I hope you enjoyed it anyway. For now, I'm Hathy, and I will see you in the next video.